Hey guys, I'm going to do, I've broken this lecture into three parts. So we'll do a basics kinetic review, and then we'll do aminoglycosides, and then we'll do vancomycin. So it'll just be a quick review. You've seen these slides before. This is what we did last year, but just kind of a hit the high points review to help you remember how to do kinetics. Okay, so why do we monitor blood levels? If we when we know that there's a relationship between serum concentration and a pharmacological response, and when the drugs are dangerous. So we've got drugs like gentamicin, tobramycin, vancomycin. Those are the ones we're going to focus on today. But there is a whole list of other. This is not an all-inclusive list that you have on your slides here. But we use them to help us predict toxicity as well as efficacy, especially when there are drugs with a narrow therapeutic index. So let's just remember that when drugs in the blood, it's going to, in this little graphic over here, we will kind of hit an equilibrium point where the drug in the blood goes back and forth between the tissue. So that's why we can sample the amount of blood the amount of drug that's in the blood to kind of determine what the concentration is at the tissue site. This slide is just a list of commonly used abbreviations. These T's, just mind your T's because they do get a little bit confusing. So pay attention to what kind of T you're using. Okay, so let's review volume of distribution. That is the extent, that's where the drug goes out into the body. So the volume of distribution is equal to the dose over the concentration. Okay, so it's going to be milligrams or dose over milligrams per liter. So your volume of distribution should be units of a liter. Drug clearance, that's the amount of volume that the blood completely clears of the drug per a unit of time. Okay. Elimination rate is KE, and that's the fraction of drug that's removed over a unit of time. So here's your KE formula. It's the natural log of the initial concentration over the second concentration, and then the difference of time between those two concentrations. And then the half-life is, the formula for half-life is 0.693 over KE. And that's the time that it takes to get rid of half or 50% of the drug that's in the plasma. Not the dose that was given, but the drug that's remaining in the plasma. So the volume of distribution, again, it relates the amount of drug in the body to the measured concentration in the plasma. This should be pretty constant. A large volume of distribution means that the drug distributes out. A drug, for example, would be digoxin. It has a very large distribution. It goes out to that skeletal muscle. A small volume of distribution, an example would be aminoglycosides. So I like to think of volume of distribution as kind of the way it stays. If it's a small volume of distribution, it's going to stay close to the blood. If it's a large volume of distribution, it distributes out to the tissue. Drug clearance. So clearance and volume of distribution together determine a half-life. The clearance is the volume of blood that's completely cleared of drug per unit of time. So your units are going to be volume, mLs per minute, or per hour. We use mLs per minute mostly. And so again, you can see how we go from elimination. The elimination over time removes concentration from the blood. The elimination rate constant, again, is KE. That's the fraction of drug removed over a unit of time. So 0.25 hour to the -1, that's your units, to the -1, means that 25% of the drug remaining in the body is removed each hour. Okay, so that's not this is different than zero order kinetics. This is first order kinetics. So it means however much is left in the body, we're going to remove that much per hour. And you can write this formula two different ways. You get the same answer regardless of the way that you write it. The half-life is the time that it takes for the concentration of drug in the blood to be decreased by 50%. So one half-life, we're going to have 50% remaining. In two half-lives, we're going to take 50% of that 50% that's remaining, therefore we'll have 25% left. Three half-lives, we'll have 12% left. Okay, so it takes about 4 to 5 half-lives to reach steady state. And that's just a principle that you have to know. Usually a total of 6 half-lives, you should have eliminated all the drug. It should be completely gone. And again, the formula is 0.693 over that elimination rate constant. So therapeutic drug monitoring, this formula right here is so helpful, and you can manipulate this formula to use it several different ways. So this is just the straight line. So if you think about drug elimination on a first order, you've got a straight line going down. If you have one concentration point there and you know the KE, you can predict what another concentration will be in a time away from where you started. Okay, so you can use this formula to predict what your next level would be. So if you sampled blood and you had a level, say, of 15, and you want that level to be 10, and you want to know how long it's going to take to get there, you can substitute in this T value right here to try to determine when you get to that concentration that would be 10. You can use it downstream, so you can predict a concentration in the future. Or if you have like a trough level and you want to backtrack to see what the predicted peak would be, you can plug it in here, only you would change this from a negative to a positive. So if you're going back up the slope, it's positive. If you're going down the slope, it's negative. And this T then becomes the time difference between the two concentrations that you're looking at. So again, here, this is a really important formula for you. And if you understand the concept of that straight line, this y equals mx plus b, so you've got a graph and you've got 2 points where the time is on the bottom axis and the concentration is on the vertical axis. Okay, so you've got a time difference and you've got one concentration, you can find the other concentration. Okay. All right, so that's your basics kinetic. That was really fast. That's your basics kinetic review. Okay.